Hi folks! Welcome to the second part of this functions review for Math AASL for the IB program. Standard disclaimers apply. This is not produced by IBO, and it's not an exhaustive look at functions, but it's an overview of the key concepts. In the last video, we looked at sort of function composition and inverses, we looked at linear functions, and we looked at quadratic functions and equations. In this video, we'll be looking at reciprocal functions, at logarithmic and exponential functions, and at general function transformations. There are timestamps and downloadable notes in the video description, and you can make use of YouTube's many accessibility options. One of the best ways to get a lot out of the video is to pause and try the questions yourself. There are often many different ways to solve a particular problem, so if you're using a different way than I am, that's great. As long as it's valid, keep doing what you're doing. Alright, with that out of the way, let's dive in. Our first topic is reciprocal and basic rational functions. So a basic reciprocal function is 1 over x, and it looks like this. It has asymptotes on the x and y axes. It has no axis intercepts. Its domain is x, it can't be 0, and that's because you can't put 0 into this. That would be division by 0. And its range, you can see, is y not equal to 0. It has a vertical asymptote of the y-axis, and the equation of the y-axis is x equals 0. It has a horizontal asymptote of the x-axis, and the equation of the x-axis is y equals 0. So you can see that the asymptotes correspond to restrictions in the domain and range. The type of rational or fractional functions that we'll be looking at in this course are of the form linear over linear. And they're just transformed versions of 1 over x, so they have the same shape. They have the same features, but they can be trickier to decode. We're going to assume that the top and bottom do not contain the same binomial factor because other shenanigans might ensue, but typically they don't. So we're going to need to be able to describe what's going on with the axis intercepts and the asymptotes for these rational functions. And there are rules, like these ones over here. The y-intercept, if you have something in the form ax plus b over cx plus d, the y-intercept is just b over d. And the x-intercept is negative b over a. And the horizontal asymptote is a over c, and the vertical asymptote is negative d over c. If you want to memorize those, that's great. For me, I know that I'm just going to botch them when the time comes, so I want to think a little more conceptually about them. A y-intercept is always found by subbing 0 for x. An x-intercept is always found by subbing 0 for y. For a horizontal asymptote, I'm just going to imagine what happens as the x values get large, because if we go out towards infinity, that just means an x that is big. And the y value that we approach will be the asymptote. So we can think of the limit as x goes to either positive or negative infinity, and we can do that informally. Lastly, for the vertical asymptotes, I'm wondering what x value makes the bottom 0, or what is the domain restriction? Whatever that is, that's going to be our vertical asymptote. And again, we're assuming that we don't have the same factors on top and bottom. So let's check that out in the context of an example. We want to find the key features of this function. So I'm going to start by finding the y-intercept, because it's pretty easy. And I find that by subbing 0 for x. And I can see I'd get negative 3/4. Again, you can use the rules if you want, but the y-intercept is the point 0, negative 3/4. If I want the x-intercept, I sub 0 for y. Now that's a fractional equation, so maybe I'll just times both sides by x plus 4, and that will let me figure out the answer. On the left, I'll still have 0. On the right, I'll have 2x minus 3, or 3 equals 2x, or x is 3 over 2, or 1.5. So the x-intercept is 3 over 2, 0. Some people might look at that fraction and just say, well, the x-intercept is going to be whatever makes the top 0, and that's a pretty fair way to look at it as well. In fact, secretly, that's what we've done. Our equation turned into the top equals 0. Now, if I think about this function, what is its domain? Well, I know that the bottom cannot be 0. So x cannot be negative 4. That is the domain of this function. That means that the vertical asymptote is wherever that domain restriction is. X equals -4. We could even start to sketch at this point. So at x equals -4, there's a vertical asymptote. There is a y-intercept at -3/4. There's an x-intercept at 3/2, or 1.5. The last piece of the puzzle is going to be finding the horizontal asymptote. So you can learn it as rules, as just that 2x over x gives you 2. You can think of it formally in terms of calculus terms, lim as x goes to infinity. Or you could just imagine what it's going to look like if we put in a big x value, like 1,000,000 in there. What y value are we going to tend towards? And I'm not going to grab my calculator to figure this out. I'm just going to think about it. The top of that fraction is about 2 million, a little less. The bottom is a little more than 1 million. 2 million-ish divided by 1 million-ish is 2. So the horizontal asymptote is just that y value that we're tending towards as x gets big. Will be y equals 2. Again, if you prefer to do it with some rules, go for it. It's worth noting here that vertical asymptotes are x equals, horizontal asymptotes are y equals a constant. If you write vertical asymptote equals -4, then you won't get the marks. So in the end, here's what this graph looks like. It's going to be one of those sort of butterfly-looking graphs that we saw already that heads out towards that asymptote. And then in the other half, it's going to look like this, still bounded by those asymptotes. Once I find that horizontal asymptote, I can also say that the range is going to be y is not equal to 2. The next topic that we're looking at is function transformations. And this is a biggie. It says for any function f of x, the following rules explain how a transformed function compares to f of x. So if you replace x with x minus c, no matter what the function is, then you're just taking the basic shape of the original and shifting it or translating it to the right c units. And I know it's annoying that x minus c sends it to the right. All the horizontal transformations are annoying. If you had x plus c, that sends it to the left c units. Okay, let's assume c is a positive number. If we have instead a number tacked on to the very end, so this is kind of like y equals f of x plus d. Well, the y value is just increased by d, so in this case, it shifts it up d units. If you have f of x minus d, then that's going to shift it down d units. The vertical transformations are more intuitive. A plus means up, a minus means down. If you have your function multiplied by a number, like this, p times f of x, and all these letters are arbitrary, you may have learned them with different letters, you may run into them with different letters on the exams. This is a stretch by a scale factor of, really should say absolute value of p, because we always say our scale factors as positive numbers. Now what happens if you have a negative value for p is that it causes a reflection through the x-axis. So let's just take a look at what that means. If I had some point A and I flipped it through the x-axis, instead of being above, it would be below. Now let's suppose we have f times something multiplied by x, so q of x. That's going to stretch it horizontally by a scale factor of not q, but of 1 over q, the reciprocal of q. And that's annoying. And again, like I said, the horizontal transformations are annoying. They're less intuitive. A negative q value causes a reflection through the y-axis. So if I took that A point, again, and I just reflected it through the y-axis, that would not change its height, but it would change its position left to right. These transformations can be combined. If the function is presented in this kind of form here, and again, the letters are arbitrary, but the thing to notice about this is that the coefficient of x is sort of factored out. Okay, so you have q brackets x minus c. If you have it like that, the translations happen last. The order in which the reflections and stretches happen in doesn't matter because a reflection and a stretch is really the same kind of operation. It's a multiplicative operation. whereas a shift or translation is an addition or subtraction type operation. Let's take a look at this in the context of a few examples. This first one says, consider the graph of f of x shown below. It's some weird shape. On the same grid, sketch the graph of negative 2f of x plus 3. So the first thing I'm going to do is catalog my transformations. A negative out front is an x-axis reflection. This 2 represents a vertical stretch by a scale factor of 2. Or if you're just writing it informally for your own benefit, you can just say times 2. And lastly, this x plus 3, that's a horizontal translation. 3 units to the left, which again is annoying, but x plus 3 means it sends it to the left. There are a few ways we can do this. I'm going to go through it 2 different ways. One just graphically, and one using mapping notation. You can do whichever one you prefer. I'm going to label these points A, B, and C. I'm going to take A, and I'm going to flip it through the x-axis. That would put it right here. And then I'm going to stretch it by a factor of 2. So right now it has a y value of negative 3. I need to make it twice as tall, so it's going to have a y value of negative 6. There we go. And finally, I'm going to move it 3 units to the left. 2, 3. That's its final location. I'm going to call that A prime, or the location after all the transformations. And I'm going to get rid of all the scrap work on the way. I'm going to do the same thing to every other point. So B needs to be flipped through the x-axis. That would put it right here. It needs to be twice as tall. So right now it has a y value of 4. It needs to have a y value of 8. And it needs to go 1, 2, 3 to the left. And that's the location of B prime. Lastly, I'll take C, which was above the x-axis, and flip it below the x-axis. I'll make it twice as tall, so its y value is currently negative 1. Now I'll make it negative 2. And I need to send it to the left 1, 2, 3 units. That means it will end up right here. I'll get rid of my other little pieces of work on the way, and I'll call that C prime. And now I just have to connect them up. A connected to B in a straight line, so I'll just do my best here. And B connected to C in a curve, so something like that. If we're able to do these just geometrically like that, great, we're done. What a lot of people like to do, though, is to make a mapping rule. So they take these 3 pieces of information here, and they turn it into a rule for what would happen to points x, y. If I flip something through the x-axis, that means its y value is going to become negative. So I'll have a negative y. If I have a vertical stretch by a factor of 2, that means its y value gets twice as big. And if I send it 3 to the left, well, I know it looked like an x plus 3 in the function, but what it really does to a point is subtract 3 from the value of that x. And so that's a rule for using this transformation, or these sets of transformation, for any point. Now I think, what are the points that I had to begin with? Well, I had a point of A, which if I really look in here is at negative 4, 3. B is at negative 1, negative 4, and C is at 3, 1. If I apply these rules to those particular points, so let's take the first one, which was point A. Negative 4 minus 3 gives me a new x value of negative 7. Negative 2 times y, so that's negative 2 times 3, gives me a new y value of negative 6. And that is exactly this point over here, negative 7, negative 6. Similarly, for the point B, negative 1 minus 3, so I'm just applying this rule over here, gives me negative 4. Negative 2 times negative 4 would give me positive 8. And guess what? That's the location of this new point over here. And lastly, 3 minus 3. So again, I'm just applying this rule. Gives me 0. And negative 2 times 1, because my y value here is 1, would be negative 2. And there's the location of my last point. So at this point, I can see that it gives me the exact same result. Okay, line between A and B, curve between B and C. Hey-yo, we're done. You can do whichever method feels most comfortable for you. But when things get rough, often having the mapping notation in your back pocket can help. So here comes another one. The point A, which is 3, 1, is on f of x. Find its image on f of 2x minus 3. So let's think about what those transformations are. This is a horizontal stretch by a scale factor of 1 over 2, by the reciprocal of this. Okay? And this is a translation down 3 units. Now that we have that info, I think you can probably just think, okay, half is wide. Well, it was 3. Half of 3 is 3 over 2. 3 units down, well, it was at 1, so it goes down to negative 2. If you wanted to build a mapping rule out of this, you certainly could. You'd be told that you're getting half of x, so that's horizontal stretch by a scale factor of a half, gets half as big, and y minus 3. If you plug in that original point, that would give you 1 half times 3, or 3 over 2, and 1 minus 3 is negative 2. Okay. Same answer whether we do it by inspection or just imagining it, or whether we do it with the mapping rule. Alternately, you could just draw the grid and do it that way. The other thing we might be asked for is to give a full geometric description of the transformation, and we've been doing that in the last 2 questions. So let's just take a look here. We've got g of x is negative f of x minus 3 plus 1. So what do these things tell us? They tell us that we have an x-axis reflection, or maybe a nicer way to say that is a reflection through the x-axis. And then we're heading to the right 3 and up 1. So let's use nice terminology here. Translate right 3 units and up 1 unit. One thing to watch out for is if you have a scale factor that you're multiplying by, or a stretch, you don't want to say vertical stretch by 2. You want to say vertical stretch by a scale factor of 2, if that's the appropriate scale factor. The important word in there is factor. That lets us know that we're talking about multiplication as opposed to addition and subtraction. The last topic that we're going to look at is exponential and logarithmic functions. So here are our 2 most common exponential and logarithmic functions, y equals e to the x, and y equals the natural logarithm of x. E to the x has a horizontal asymptote of y equals 0, and y equals 0 just means the x-axis. Y equals ln x has a vertical asymptote of x equals 0. So that means the y-axis. Exponential functions have a domain of all real numbers, and they have a range, if they're not transformed, of y is greater than 0. And you can just see that on the graph. Logarithmic functions, on the other hand, have a domain of x is greater than 0. And a range of all real numbers. And again, you can see that on the graph, but it's also very fishy that those look like x and y just switch positions. And that's what happens with inverse functions. X and y switch. It's worth noting here that when we look at y equals e to the x, we're going to have the same shape as this anytime we have a base that's greater than 1. We'll have what looks like growth as we move from left to right. If we were to have a base that is smaller than 1, so between 0 and 1, then we'd have a decay function. But of course, that could all get messed with our transformation rules that say that you can have reflections through x and y axes. If you're ever really in doubt whether you have a growth or a decay function, really if you get 2 points, then that will tell you whether you're growing or decaying. So we're just going to play with a function here. F of x is 2 to the 3x minus 5. We're going to find f of 1. All right, no big deal. F of 1 would be 2 to the power of 3 times 1 minus 5, or 2 to the 3, that's 8, minus 5, or 3. So f of 1 equals 3. Next, we're asked to write the equation of the asymptote. And I'm going to do this just by quickly sketching the graph. Here's something I know about it. It has a minus 5 at the end, so things are going to move down 5. And this really answers my question about the asymptote. The asymptote's been moved down 5, so the equation of the new asymptote is y equals negative 5. One thing worth noting here is that when we say f of 1 equals 3, that means that the point 1, 3 is on the graph. Okay? Or in other words, when x is 1, y is 3. Now, I'm not going to worry about doing an amazing job of sketching this. I don't know where the axis intercepts are. I could find them. But the basic look of the graph is going to be something like this. C says to write the domain and range. So the domain is all real numbers. You can put whatever number you want into this function. If you think back to our very first slide, there were some things that limited domain, division by 0, even roots of negatives, and logs of 0 and negatives. This exponential function contains none of those issues. Therefore, its domain is all real numbers. It has no illegal stuff in it. The range, you can just see from that little graph that we made, is y is greater than negative 5. All right, moving on to the fun stuff. Find f inverse of 3. So let's think about this. Before doing a whole bunch of switching x and y work, which we can do and we will do in E, I want to walk you through a little hack in this question. They're telling you that this is an x value on the inverse. That means that it is a y value on the original. So rather than finding f inverse of x, what we could do is we could just put that 3 in for y, or for f of x, in the original. So we could say 3 equals 2 to the 3x minus 5. Or 8 equals 2 to the 3x. I think a lot of people at this point will see that the answer is just 1. But we could keep going. We could say, that's 2 to the 3 equals 2 to the 3x. Drop our bases. X is 1. We actually already knew what the x value is when y is 3. Right over here. It said when y is 3, x is 1. Okay. So there are some little hacks we can use here. But if we don't notice them, then we can just trust our mechanics or do part E and come back for part D. This little hack, though, that when they tell you the x value on the inverse, they're telling you the y value on the original, or vice versa, could be pretty helpful. The last question says, find f inverse of x. So I'm going to give myself a little extra room here. The original function is f of x equals 2 to the 3x minus 5. F of x just means y, so that means y equals 2 to the 3x minus 5. If we want to find the inverse, we switch x and y. So on the inverse, I'll say x equals 2 to the 3y minus 5. And now I have to isolate that y. So maybe I'll move the x over here, and I'll get x plus 5 equals 2 to the 3y. I know that the answer here is going to be a logarithmic function because exponentials and logarithmics are inverses of each other. But I have a bunch of different techniques that I can use to get there. I'm going to show what I think is the slickest possible answer first, but then I'll give a bunch of other possible ways that you could deal with this. So what I'm going to do is I'm going to think that this means a logarithm with a base 2 of x plus 5 equals 3y. That's using the idea that a to the x equals b is equivalent to log base a of b equals x. Just changing forms. You may have other mnemonic devices that you use to help you remember that. We're just switching forms. And again, this is not the only way to deal with this one. And now I can just divide by 3. So I'd have log base 2 of x plus 5 over 3. That's our inverse function. F inverse is log base 2 of x plus 5 over 3. I mentioned there are other ways of doing this. I think they all rely on getting to this second step. And then if you wanted to, you could just take the log base 10 of both sides and say log of x plus 5 equals log of 2 to the 3y. And you could use your power rule and bring down that 3y. And then you could divide by 3 log 2. This would be another way that you could write the answer. And that would be y equals, which is the same as f inverse. You could do the exact same thing using natural logs. So ln of x plus 5 equals ln of 2 to the 3y. Bring down that 3y using power rule. And then divide by 3 ln 2. With that in mind, I'm going to show a bunch of other ways that you could write the answer, but really, any of these are absolutely fine. Wow, that's a lot of different possibilities. I think the one in blue is the best. There are actually other ways that you could write it as well. If nothing else, I think this proves the value of having a show that question, where you know what form you're leaning towards or what one you're trying to get to. It's also worth mentioning here that if you wanted to answer the question from before, which was to find f inverse of 3, well, you could plug it into any of these forms. You could put it in here, log base 2 of 3 plus 5 all over 3. That would be log base 2 of 8 over 3, or 3 over 3, and we'd still get that 1. And that would be true from any of these forms. Okay, one last one, where we're going to think about a logarithmic function. And we're asked for the domain of g of x here. And this was one of our log rules. If you have the log of something, that something has to be positive. You can only take the log of a positive number in the real number system. So for us, the something that we're taking the log of, and we're taking a natural log, is 2x minus 5. That thing has to be greater than 0, which means 2x has to be greater than 5, where x is greater than 5 over 2. That is our domain. You can find it by inspection if that feels better for you, but this is a nice little technique where you take whatever's inside the log, set it to be greater than 0, and solve. Write down the equation of the asymptote. The asymptote is on the boundary of the domain. Therefore, the equation of the asymptote is just going to be x equals 5 over 2. This graph will basically look like this. Here's 5 over 2, or 2.5, and it's going to be some kind of curve that comes up like this. I haven't put where the axis intercept is correctly, but that's the general look of it. Lastly, we're asked once again to find an inverse. So you're probably thinking, oh no, that last one had a lot of possibilities. I think this one will be more straightforward. So the original means y equals ln of 2x minus 5 plus 1. The inverse tells us to switch x and y. So we will have x equals ln of 2y minus 5 plus 1. And our goal is to get y on its own. Let's move that 1 over. And now we have to somehow break that y out of the logarithm. And the way to do that is to switch to exponential form. Again, we have this property. A to the x equals b is equivalent to log base a of b equals x. When we're dealing with natural logs, the base is e. So e to the x equals b would be the same as log base e of b equals x. And log base e of b is what a natural logarithm is. It's ln b. So when we see ln of 2y minus 5, that means our base that we're dealing with is e. Our power that we're going to have, in this case, is going to be the x minus 1. And the result will be 2y minus 5. Let's keep working this through. I'm going to add 5 to each side. And I'm not going to add it to that minus 1 because it's up in the exponent. And lastly, I'll divide by 2. So y is e to the x minus 1 plus 5 all over 2. If we go to our nice notation, that means g inverse is e to the x minus 1 plus 5 all over 2. Not surprisingly, the inverse of a logarithm was an exponential function. That brings us to the end of the major topics in functions. I hope this has been helpful. Good luck with the material, and take care, folks.